I want to continue today with power management followed by aerodynamics. There's a lot of content here that due to time I'm going to try to go quickly with. I'm really trying to whet your appetite for the things that you might ask yourself. The presentation will obviously be available to you. I will be available afterwards as well for questions, but I'm going to try to be efficient in my presentation here. Okay, so when you think about power management, it's really looking at how much power does it take to get, down the road, how to most efficiently use the solar energy that you collected and convert it into miles, right? We do not get, credit for the amount of energy you collect. You only get credit for completed miles on the solar car. So how do we most efficiently get to use that power? And that depends on aerodynamics and rolling friction and weight and resistance, and we'll talk about that in the next section. But before we do that, I want to talk about power itself and what solar cars get. So a typical car, especially in the classic division, will probably get something on the order of 800 to 1,000 watts of power from their solar array. From there, you might start calculating and saying, well, you have about 12 hours of sunlight that's available to you. So at the ends and the beginning of the day and end of the day, you might have less. So that's why we say approximately 12 hours. And so you'll essentially have 9,600 watt hours to play with on a given day. And of course, that's assuming that you have clear skies, good sun, you're aiming your solar panels in the right way, you're doing the most efficient thing you can, okay? If you size your battery pack to be a little under the rules, you might size your battery pack at 4,000 watt hours of energy. So you're getting 9,600 watt hours, over the course of the day. You get 4,000 watt hours in your battery pack. That's, pretty good. You can get, 2 cycles through. But the key point of this slide is it takes approximately 5,000 watt hours to completely recharge the battery pack. The point here is as you start filling up your battery, if your battery is completely empty, it's very easy to to collect more energy. It's very easy to charge. As you continue to fill up the battery, at the last little bit, it will take more energy to fully charge that battery than one-to-one conversion. And so that's why we have that particular note there. So it's something to think about in terms of your power management is, how full do you get your battery compared to, if you keep your battery lower, then you might get more efficient use of that battery. The other things, a dead battery is dead weight. If you kill your battery, it does not give you any more usable energy left, and you may not even recharge. Now you're just carrying it along with you. It's just dead weight. A note here, right? Experienced solar car teams know this, but your battery is not dead at 0 volts, right? You're looking at something on the order of 10.5 volts for a 12 volt nominal battery where you're really dead, okay? And so you only really have a certain range to play with in terms of voltage. It takes about 5 hours to completely recharge, and then of course you got to consider hills, clouds, tree, wind, children with sticky fingers, basically anything that could block the solar collection on your array. We talk about shading and how that affects your series of cells. And so, you got to keep an eye on that and consider that as part of your power management thing. We talk about 9,600 watt hours of energy that you can get from the sun. You're not going to get that because of all these other considerations. And so how do you know how much energy you have to play with in a given day? You have to test for it. In our teams, as we buy the solar panels, we will actually bring it outside and we will record over the course of the day how much energy that you get throughout the day. And you would do that over the course of days so that you can get a running average, right? You want to do this on cloudy days to see what's the effect of clouds on your collection. You may want to start angling your array to different angles and see what the effect of that is. You want to know as much data as you can. Okay? And then, of course, that's the production side. On the consumption side, you have to say, how much current do you draw at any particular speed, right? It is not linear. Running at twice the speed does not mean you use twice as much energy. It's exponential. So typically, it's 4 times as much or more to run at a faster speed. And that's cruising speed. That's not the effect of acceleration. Okay? So let's take a look at that in more detail. The very first thing in power management is you have to come up with a strategy, right? What is your ultimate high-level decision you're making with regard to the running of your car? You may, without looking at all your inputs and outputs, decide that your strategy is that you want to run your batteries dry every day and recharge as much as you can in the interim period, right? You race from 9 to 5 of a break in the day, from 12 to 2 of your classic division car, or you get 9 to 5, all day for an advanced division car. Well, there's hours after that, right? After 5 o'clock and before 9 o'clock, you have charging time. So you may choose to run your batteries completely dead and then charge it up and get whatever you can. Unlikely to get all the way up to the top, but you'll get a good efficient conversion because batteries charge better when they're dead, right? You could say, well, I can calculate how much energy I get from 5 to the end of the day and from before 9 o'clock the next day. I'm just going to drain the battery so that at the end of the day, I have enough capacity that at the beginning of the next day, I'm fully charged again. That's another possible strategy. You could also say, well, the event is, let's say, 4 days long. Maybe by the end of the day, on the first day, or maybe the beginning of the second day, I want to be a quarter of the way down my battery pack. And then the next day, I want to be halfway down my battery pack, so that by the end of the race, at the end of the day, I'm completely dead. You could do that too. There's all sorts of questions that you want to ask yourselves in terms of strategy. Come up with that first. Then we'll do the math as to how fast you might want to run and so on. Okay? Do you run based off of net draw or motor draw? So once you decide on your high-level strategy, do you calculate that based off of, I'm just going to pull a certain amount out of the battery, that would be the net draw? Or do you try to drive the car based off of how much a driver, you say, go expend 30 amps, and that could come some from the solar, some from the batteries. You have to make that decision and then calculate based off that decision. But, as I said, there are no right answers, just decisions. Every team has their own thoughts of doing it. There's no they're the team that does it best. It's really, you have to make the decisions, and there's no wrong decisions. You just have to experiment and give it a try. And this is the fun part of solar car racing, right? Not that building isn't fun, but the strategy part is a lot of fun as well. Okay, so once you get your strategy, how do you convert that to actually running of the race? So I will pose a question. If your strategy is to empty your battery pack each day, and you have a 100 amp hour battery pack, how fast should the driver drive? Can anyone answer that question? Jerry can answer that question. What is that, or you can answer that question. How fast?
Well, it would depend on, say, how much battery they have and how much they're willing to use.
Yeah, it depends. Do you have an answer, Jarrett?
Approximately 12.5 amps.
12.5 amps. Well, I said how fast should the driver drive? And the trick question is, you don't know how fast they can drive because there's no speed. It's really not dependent on speed. You shouldn't be telling your driver, drive at 25 miles per hour. You should do essentially what Jared said and say, drive according to your current draw, not your speed. Okay, so how much current should you be taking? So 100 amp hours, 6 hours of racing, 16.7 amps, right? That's a nice division, right? Is that the right answer? No. Why is that not the right answer? Okay, you have to deal with the Pugh-Kurtz equation and how you're going to draw it much more than that. I didn't take that into account here, but that's correct. But you also have to consider that you have 2 hours of charging in between. So, your 16.7 assumes that you're not getting any charging going on. And so if you calculate for the idea that, let's say you have a 1,000-watt panel, 48-volt system, 2 hours of charging, you get 40 amp hours back. And so you can actually calculate and say, you can run, if you ran 16.7 amps on the beginning half of the session, you could essentially run 30 amps at the end, the second half of the session, excluding the Pugh-Kurtz equation thing. So that's not really a good way of running, in an even manner. You really want to try to be more constant in your current draw. So to get the same current draw, what would you have to do? You would add that 40 amp hours into there. You would be averaging 23 amps or something like that. So this is the type of math that you want to do. Again, I forgot to include the Pugh-Kurtz equation, so I'm going to have to add that in later on in this presentation. But just to get an idea of these are the things you have to think about. Once you decide on a strategy, this is how you calculate it, and this is, to the driver, all they should know is, I want you to drive 23 amps. That's how fast they go. Okay, so in order to do that, how would the driver know to do that, right? So you need to be able to have some information available to the driver. A voltmeter and ammeter might be useful. An ammeter is very useful to tell you. If you tell the driver, you got to drive 23 amps, well, how are they going to know? They need to have some meter that tells them, I'm drawing 23 amps. Batman is this instrumentation thing that you can put in your car that will tell you volts, current. It actually counts in your amp hour counter as well. So it gives you the capacity of your battery. The Link 10, or what used to be called the E-meter, is another meter that provides that type of information. The Walnut team used the E-meter, Link 10 meter, and what was neat is we were able to pull instrumentation off of that E-meter into a computer and process it. So there was telemetry data that we could collect during the course of the race and transmitted via Jared's description of connection to a computer, which then went to a cell phone and sent over cellular to a base station, all the data of how the car is operating. And I will show you data, real data from the Walnut team to come. Okay, so what data is important? Of course, you want to collect different amount of information based off of your decisions that you make. I feel like there are critical measurements like the battery voltage, the motor current draw, the array current, and then your capacity. Those are really the critical pieces of information. There may be others like temperature that you may consider doing to adjust for how the batteries operate. Okay, so as I said, in the Wellness Solar Car team, I'm offering this information to you because, well, they don't exist anymore. So this is real data from their electric solar car on July 21st, 2017. What's on the graph here is the system voltage in orange, the current in blue, and the power, basically the multiplication of those two, in gray. The gray one has this particular column of data. The voltage and current is over here. We had a 48 volt car, and so really max is going to be 57.6 volts is full charge. I would say when you look at this data, and these are just charging characteristics, so I only showed you the charging side, not the discharge side. What's interesting about this data? Well, first, you'll notice that at some period of time it goes to 0. That represents time that we spent swapping the batteries. Okay, so you'll see that this is one battery pack, another battery pack, another battery pack. So you'll also see that, we spent probably a little under an hour using up our first battery pack, and then our time got shorter and shorter, and then somehow we got a long time there. Just a different data point. You'll also notice that the charge, that's the voltage keeps going up. That's nice. And then, we're ready to be full there, and then we decide to swap. Other points. So you can tell that in gray, the power input that we got was fairly constant throughout the racing period. There's some indications over here for other reasons, and we'll get to that. But, from 9 to noon-ish, we basically got 1,000 watts of input. I will say that this occurs because we were in the electric solar division with this data, which means you have some person or some automated mechanism of making sure that the panel faces the sun at all times. And so that's why you get a more constant charging input. If you didn't have that, if you were on a solar car, as the day progresses, you will get more energy until 2 or 3, and then you'll start dropping off in power. Well, you will also see that as the battery gets fuller and fuller, the power that you're really getting into the batteries drop. And that was essentially what we said is, as the batteries get full, it takes more power to drive in, and the gray is just indicating how much power is received by the battery. The battery voltage remains fairly stable, and that's expected. You expect that the voltages stay in a very good range, and it's really the current that tells you how much capacity you're able to get. And you'll also see that because of the power tracker tracking your battery voltage, it will adjust and charge accordingly. So those are some data points there. Now, on the discharge side, this is an XY plot of our speed versus current draw. So vertical axis is speed, horizontal axis is current draw. What do you notice about this data?
That abomination right there.
This abomination right there. As Jarrett had said in the previous presentation, this would be imprecise, right? It's got such a wide range. I can go 20 miles per hour, let's say 25 miles per hour, and I can expend 12 amps. I can expend 88 amps. Why is that? Exactly. Your speed and your current draw aren't necessarily associated as much as your acceleration and your current draw. So most of these outliers are really acceleration to your speed. And then this massive information is more of your cruising speed and how much you're expending for the cruising speed. And the variance here could be explained by sort of ups and downs on the track. So just something to think about. Like I said, current draw is not directly associated with speed, and you got some outliers primarily for acceleration. So, why do I bring up this data? This data is really to tell you, unless you're able to test for this, you can't do the calculations you want. You can have a high-level power management strategy decision, but you can't get to how fast do I want the driver to be driving, how much current draw do I want them to be expending. That's something that you need to test for. So, how do you get the right data? You gotta test. And you gotta take multiple runs at different speeds. So, we typically, there's a question about where do you test. One that was working out of a shop that was in an industrial area. We worked in the weekends, so we just drove up and down the same road. And so it was a nice, constant, controlled environment. And we had a slight uphill in one direction, a slight downhill in another direction. And we would say, okay, run the car 20 miles per hour. And we would collect that data. And we would take 10 runs at it on the same day. And run the other way, downhill, 10 runs that way. Now run at 25 miles per hour, and so on, so that we can correlate at cruising speed how much current we would be running. Once you got that, you get an idea of how to actually run, so that, like I said, amps don't mean anything. You got to convert it into laps, into miles. And so speed makes a difference. And so you can find out what's the most efficient use of your car, at what speed is most efficient for your car. After that, run simulated race days. Have a full day that you plan to be at the shop and say, okay, we're going to start at, break out of impound at 6 a.m., charge the car up for a period of time, start running at 9 a.m., take it off at 12. Do everything that you would if you were racing here, and try to practice to make these strategic decisions. As you get more data, as you see that there are clouds in the way, as you see a better performance in your car, you need to be able to adjust your tactics, right? You have a high-level strategy, but you got to convert it into tactics. Say, run faster, run slower, draw more, draw less. So we talk about making decisions. This is a picture of the pit area that your team will be based out of. The cars will be out on the track, but you'll have a dedicated spot for your team, and this is what we call our base station. We have a telemetry system where we collected all the data. We can see in real time how much current we're drawing, how much current we're getting from the solar panels, what the estimated time left on a particular battery based off of our current draw. We program all that into our systems so that we can make certain decisions. You may not have those things. You may just be radioing your driver, collecting for your amps and volts and all that stuff, and that's okay. Either way, you have all the data in front of you, and you can make decisions based off of that data. Okay? Your driver should not make any decisions other than driving. It's funny, in my teams, people actually don't want to drive because they essentially become a robot. The base station, the command center will say, hey, drive at 20 amps. And they got to drive at 20 amps. The fun part is making decisions over on the strategy side. Now, some people like driving on the track. It's sort of neat, but I have fun with the strategy stuff. And so, we talk about on the pit crew doing the calculations, looking at the data, telling your solar car, speed up, slow down, drive at a higher current draw, lower current draw. that's really how you should run the race. The other key part, only one person should communicate with the driver. If you have radio communications and you're just going and everyone's trying to give their inputs, you may have one person say, go 25 amps, no, go 30 amps. The driver gets confused. You want to make sure you have a point person. You make your strategy decision, then you tell the driver, okay? And then we talked about telemetry. So that's sort of the telemetry side, the strategy decisions you have to make. But as a part of testing, you also note that, as I said, motors operate at a particular RPM that's most efficient. So you can calculate for that on paper, but the best way to know is to test. And so you want to have the ability to have different gear ratios. And especially on the road, you may consider having different gear ratios per day based off of uphill or downhill things. But even on the track, you want to be able to figure out your gear ratios and find out which gear ratio is most efficient for the speed that you want to run. Of course, when you gear it, you may want to say, oh, I really want to go 50 miles per hour or something fast like that. But you saw the data that Jarrett presented. The winning teams are not driving 50 miles per hour, right? So if you drive that fast, you're just going to burn out your batteries and then you'll be parked and charging. So be realistic and then choose the gears that match a more realistic speed. Also make sure everything is all lubricated, efficient, aligned. That way you can test according to the most efficient things. So this is a pretty common ratio, a fairly small sprocket for the motor and a fairly big one in the back, and that's geared for 36, which is fairly high. In our solar car at Walnut, I think we have a 13:108 ratio. And so that actually gets us max speed to even lower than that, because your motors tend to run sort of at 5,000 RPM is a sort of a nice value for most motors, but you should look at your motor curve characteristics and find out the most efficient RPM. But then you just do the calculation based off of your wheel size, and then you do your gearing ratios to get your appropriate speed. So that's another part of power management that you have to do early on, right? Before you get to the race, you should be deciding that. And so these are places that you can get different custom sprockets so that, in case you can't get a sprocket that's of the right size, it was difficult to get a 108 tooth sprocket, for example, you can go get something made like that. Okay, other power management considerations. We did calculations, we showed you from a high level strategy, you've made a decision, you've derived how to calculate for it into day-to-day tactics. What else do you have to consider? You have to consider weather. If you get clouds, how much does that affect your power input? Right? Do you get half as much power? Do you get less than half as much power? You have to figure out that as part of your test before you get to the race. How much power do you get at different angles of the sun? So you should look at, at different times of day, and also based off of your angle of your car, you have to look at how much energy you get. Different race shapes, that's the whole, if you have an aerodynamic body that has different sides to it, how does that affect your charging? How does the route topology or track layout affect your power usage? As you go, let's say last year we went to LA, we go in an east-west direction. Well, how does that affect power compared to if you went north-south? So that's something to consider. And then, other considerations. These are just things you have to think about. How does it affect my input? How does it affect my output? And so just sort of work through some of that. Make sure you take the time during the year before you get to the race. I know you're busy building your car and making it work, but make sure you start having these discussions on your team before you come to the race. Then you can get the right data to make the right decisions. Any questions on power management?